Okay. So thank you very much. So I think we all look forward to the excursion tomorrow. But today we continue with the scientific sessions, and our first speaker today is Jens Wiebe from the University of Hamburg in Germany. And Jens is going to talk about the search for large topological gaps and isolated Majorana bound state in atom-by-atom fabricated Yu-Shiba chains. Jens, the floor is yours.
I hope you can hear me. Yes, okay. Thank you, Steffen. And thank you also, Dept, for putting together this nice series of talks and for that I'm able to show our results. I will talk today about the topic of spin chains, which are assembled atom by atom on the surface of a topological insulator. And as you might have heard on Monday by Roland Wiesendanger, we are able to, by using a scanning tunneling microscope, to measure these end states and also to show that the band structures, some of the bands in the Yu-Shiba bands of such chains are topologically non-trivial. And so today I would like to focus on think about how we can increase these topological gaps here, because one problem that we still have is that these Majorana bound states here are still quite extended along the chain, and then they can hybridize the two Majoranas from both ends, and they split off from the Fermi energy and are hidden in these trivial bands. And because the extension of these Majorana states is inversely proportional to the gap here, if we try to enlarge this gap, we might have a chance to have, in the end, more isolated Majorana bound states. And this I will show you by looking at two different samples, niobium and tantalum. Tantalum has a 3 times larger spin-orbit coupling, and the hope is that we increase the gap there. And then, if I have enough time, I will also show you some results on a thin gold layer grown on niobium, which we also do in order to increase spin-orbit coupling. And then finally, I will show you, this is the second focus on my talk, how we can also do some tests on some trivial edge states, which might look as Majorana bound states, in order to prove that they are topologically trivial. And this I will do for antiferromagnetic chains on niobium and tantalum. So these are the people who are who are collaborators. We are doing the experiments here in Hamburg in our group. Most of the work, or all the work here, has been done by a postdoc, Lukas Schneider, PhD student Philipp Beck. And then we are collaborating here with the groups of Thoro Poske in Hamburg, and also with the group of Stefan Rachel in Melbourne, and also here with Levente Rocha, and also the group of Laszlo Schönjok. And we have funding here from some priority SFB and Cluster of Excellence, and also from an ERC of Roland Wiesendanger. All right, so to give you some introduction on how you get Yu-Shiba Rusinov states, what are Yu-Shiba Rusinov states, how you get one-dimensional topological superconductivity and Majorana bound states, I will start with the smallest building block here of, imagine you have an atom which has only one orbital with one electron, and if you put this on a superconductor, you have already seen a couple of times that then you break the pairs partly in the superconductor, and therefore you get these so-called Yu-Shiba Rusinov states, which are in energy symmetric around 0. They must not be symmetric in their intensity due to Coulomb scattering effects. And the point is that if you change the Kondo coupling of these electrons, the local electrons, with the superconducting bath electrons, then you shift these states through the gap given by this formula here. So this is the effective Kondo interaction. And now the interesting thing is, if you couple such Yu-Shiba states together, so if you imagine you build a chain, and then these Yu-Shiba states, they can hybridize, as you can see here. For example, this is the spectral function here as a function of this effective Kondo coupling, and you see that you form the bands when the Yu-Shiba states are shifting in the gap. So you form these so-called Yu-Shiba bands, and when you would measure the local electron density of states in such a Yu-Shiba band, you will find that they are all over the chain. And of course, you can then have here also some gapped, some mini-gaps opening out, which are open, which we call trivial mini-gaps in this case. And the most important thing is if you have now a non-zero angle between the neighboring spins, like a spin spiral, or you have ferromagnetic chains with spin-orbit interaction, then you can show that once these Shiba bands overlap with the Fermi energy, then there is another gap which can reopen here, and this is then topologically non-trivial. And inside of this gap, you will then get zero energy states which are located at the ends of these chains. And this is exactly what we are looking for. So you can also show that this works also for ferromagnetic chains if you have spin-orbit coupling. But then the question is, of course, for an experimentalist, how do you get strong spin-orbit coupling into your real system? And for us also another question is, what happens if the chains are antiferromagnetic? Does it also work? And then here, this is of course a model, a single orbital model. What happens with multi-orbital effects? And then always the question is, how do we distinguish topologically trivial minigaps from topologically non-trivial minigaps, or trivial end states, which you can also have close to the Fermi energy from these Majorana bound states. Okay, so of course we are not the first ones who look at such systems experimentally. So there is this pioneering work of the group of Jan Stani, these iron chains on lead, which we have already seen a couple of times. So the problem here is that these zero bias features that they observe are not on all chains in their system, and also not on both ends of the chain. And also the tuning of the system here is not possible because you can only grow them but not manipulate the chains. So then we have looked at, so these are both ferromagnetic systems in red. So we looked at these niobium and tantalum substrates because there you can really also manipulate your chains, and we have seen clear topological minigaps, as you have seen in Roland's talk, in one of the Shiba bands, and also we have shown that we find precursors of Majoranas which are still strongly hybridized. And but you can also have systems here, chromium chains, where you have trivial edge modes, as was shown in Stuart Parkin's group. Then there is the group of Nacho Pascual, which works on bismuth palladium system, chromium chains here. They didn't experimentally find zero bias end states, possibly because the chains are still too short, but you can also manipulate them there. And here there's the group, work of the group of Katharina Franke for niobium diselenide, where they also manipulate chains, but here they also did neither observe a topological gap nor zero bias end states, possibly because there are problems due to quantum spin behavior. Of course, there was then also work on spin spiral systems. This is the example here of our group, where we have looked at iron chains on the rhenium 001 substrate, and you see some end state features here, but here the problem is that it's difficult to really separate them from the trivial Shiba bands because the gap size is very small, and this is the case because of the small substrate gap. And then the question is, what about antiferromagnetic chains? So here there's so far only theoretical work, and it has been shown here in the group that in contrast to ferromagnetic chains, a critical spin-orbit coupling strength is required for realizing really a transition to a topologically non-trivial phase. And we will look at this experimentally now. So all this work has been done in a 300 millikelvin ultra-high vacuum scanning tunneling microscope system, which you can see here, which is published in this publication, and we can apply a magnetic field perpendicular to the surface. Okay, so let's look at these two sample systems. Why do we choose niobium and tantalum? So the reason is that they are next to each other here in the periodic table. They have a very, very similar crystal structure. So the lattice constant is only a very tiny difference. Or I think something is mixed up in this talk, but anyhow. So what you can also show that is that they have almost identical Fermi surfaces. They have a dz square-like surface state with similar effective mass and binding energy. And the gap of the tantalum is about half of that of the niobium. And the most important thing is here, while the electronic properties are very similar, the spin-orbit coupling of the tantalum is 3 times as large. So it's not so easy to prepare clean surfaces. We have to do flashing at a very high temperature close to the melting point, but it's doable. So you see here the surface with the steps after flashing with some residual oxygen defects, and then we deposit transition metal atoms like manganese at low temperature, and they just stick on the surface. And we have also shown that the same is possible for tantalum 110 with a similar quality. And here you see a sample of manganese atoms on the tantalum 110 substrate. And then we go ahead and the next thing what I want to show you is that these systems have very similar multi-orbital Yu-Shiba Rusinov states. So we look at the spectrum here at first for the niobium substrate. You see here the nice coherence peaks. So by the way, all these spectra are taken using superconducting tips and then are deconvoluted. And so the gap is about 1.5 milli-electron volts. And if you now take a spectrum on this manganese atom, you see that you get these additional states inside of the gap. And this is now not only one Shiba state, but 4 of those, because you have 5. You can have up to 5 because you have 5D orbitals. And then you can map the shape of these Yu-Shiba Rusinov states by taking maps at the locations of these peaks. So this is shown here. You see that we have, of course, always a peak at plus and minus energy. So you see here always these shapes appear twice. And you see that they resemble these d orbitals, right? dz square is the one which has the largest intensity here. And then there's the one which is already close to the Fermi energy is the dyz state. And here you can see their energies normalized by the gap of the niobium. So you can do the same thing for manganese atoms on tantalum. This is shown here. So now, of course, the tantalum gap is smaller. It's only 0.7. But again, you find that there's one state here, which is the dz square-like state, which is closest to the gap edge. And there are some states which are more inside of the, towards the Fermi energy. So, and if you compare the numbers here, particularly this dz square-like state is very comparable to the niobium case, and that's why it's very good system to now form bands of these Shiba states and look at their topological properties. Okay, so I think Roland Wiesenhanger also has shown already that we can investigate the magnetism of these chains by spin-resolved scanning tunneling spectroscopy. So this is just an example. We can do this for all the chains we are looking at. This is now an example of a chain assembled along the 1, -1, 1 direction. And you can see here when you measure with a magnetic tip that you can see this dark, bright, dark, bright, dark, bright contrast in a magnetic field. And if you reverse the magnetic field, you have a phase shift here of this contrast. And as you can see in the subtracted images, this reminds you of an antiferromagnet. And you can see the same thing for if you have the same manganese chain on tantalum. Again, you can see here a dark, bright, dark, bright, dark, bright contrast, which is reversed in a magnetic field. So from that, we know that for this example, both chains have an antiferromagnetic spin order, and you can really show this for more different directions, that these two systems are very similar. And here in my talk, I will concentrate on this direction along 001, chains along this direction, which are ferromagnetic, and later on chains along 1, -1, 1, which we have just seen, which are antiferromagnetic. Okay, so let's look at these ferromagnetic chains along 001. And now, again, we will, in order to see what the Shiba bands are looking like, so how these Yu-Shiba Rusinov states are hybridizing to form Shiba bands, we will take spectra along such a chain and plot here the energy, and here is the position along the chain. And then you can see that now inside the gap of the substrate, which is marked by the coherence peaks here, you can see these standing waves occurring with different numbers of maxima. So this one has 4, 3, 2, and 1. But you already can see that there is this kind of gap at the Fermi energy, and this holds true if you now make the chains longer and longer, then just your standing waves are changing in energy, okay? And the states just hop across this gap. So there is this mini gap, and we can also look at this a little further if we not plot the density of states only along this line, but on a two-dimensional fashion across such a chain. And then again, you can see these states which I've just shown you previously here with 7 maxima, 6, and so on. So because if you remember these, the form of the Shiba states, we can prove that these bands which are forming here are coming from the dz square-like orbitals, which have this kind of shape. But you can also see at some locations where you, for example, do not have these alpha Shiba states, you can also see these kind of standing waves, which remind you of the extension of these other orbital states. And so we think that these kind of states here are scattering states which appear in the other orbital delta band. And now you can go ahead and extract the dispersion of these states either by doing just a Fourier transform or by doing some more, by fitting some sine square functions basically to the data, and then you end up in this kind of dispersion of these states. So you here see again this nice quasi-parabolic band of this alpha Shiba states with this band gap, mini gap here. But you can also see that these other states, so these states here, they basically cross the gap. So if you zoom in intensity here, you see that these orbitals here, they cross the gap. And now, if you want to show that this is you can show that this is a topological gap, for example, for this alpha band, because if you compare this to a single orbital tight binding model, you see that it looks, so you can compare this to this tight binding model and go from the topologically non-trivial case to the trivial case, and you see that you clearly have this kind of crossing of the Shiba band of the Fermi energy, which means that it has to be a topologically non-trivial band. And on the other hand, this is not, of course, a little bit more complicated because you also have this delta band. And here we have to rely on theory, recent theory from Daniel Crawford and Stefan Rachel, which tell us that overall the system is topologically non-trivial. So these delta bands also must have a topological gap, which is just too small for us to be resolved. Okay. Okay. I cannot show you this. These other kind of. Sorry, I'm also doing this. I have a problem with this button on the side. Do I have to? Okay. Maybe just press 10, enter. Yeah, okay, thanks. Okay. I have no time to look into other chain directions, but the question for us now is how are we able to increase the size of this gap? Because one problem that we have here is that in the data we do not see clear n states, and then the question is, can we increase the size of the bands by using a substrate with stronger spin-orbit coupling? And therefore we do basically exactly the same experiments now with tantalum. So here I show you the spectroscopic line profiles along chains of increasing length. And again, this is the energy, this is the location along these chains, and you can see basically it's very similar behavior as before, just with less energy resolution. Yeah? Again, you see these standing waves which are jumping across the Fermi energy, so there is again a mini gap, and you can also look at the states in a two-dimensional way. Here again, you can see these standing waves with 4 maxima or 5 maxima or 2 maxima. And then you can also prove again that these states come from this alpha orbital. Now it's slow. Okay. And if you again extract the dispersion, you find again a very similar band structure here, which now has a gap, also a gap at the Fermi energy. And you can, in order to extract absolutely the width of the gap, you can make a cut through this position here and extract here the size of this topological minigap, and then compare this to the niobium case, which we measured before. Yeah, so you see here the comparison of the two band structures. So they look very similar, just that, of course, on the tantalum you have less energy resolution. And by this comparison, you can see that the gap of the tantalum is about 150 microelectron volts, while it's 160 microelectron volts on the niobium. But of course, you have to relate this to the absolute gap of the substrate, and by that you see that the gap of the tantalum is 2 times as large as on the niobium. And because these two cases have so similar electronic structures and so similar Shiba state properties and similar dispersions of the Shiba bands, we think that this strongly substantiates that this minigap is really due to p-wave pairing induced by spin-orbit interaction. All right. So how much time do I have?
6 minutes.
Okay, then we have to press the emergency button. So I have to skip this gold monolayer, and we go to the, thank you, antiferromagnetic manganese chains. So now let's look at this case of antiferromagnetic manganese chains on tantalum. Here is a manganese 22 chain, and again, I can measure line spectra along such a chain, and again, what you see is that within the gap of the tantalum substrate, you have this kind of band formation here, Shiba band formation, and then you have a mini gap, and in this case, you see some end states. Yeah, these states here are on the quite close to the Fermi energy on the end of these chains. You can also do, again, this two-dimensional mapping and show that here in the Shiba bands, these states are located all over the chain, and here at the Fermi energy, you get a clear signature of some end states. You can also show this for different chain lengths. Maybe I don't have to show this in detail, but basically these end states, they already evolve for chain lengths on the order of something like 10 atoms. Okay, so the question here, what is surprising is that this is a very large minigap, and the question is, of course, always, are these Majorana bound states or trivial end states? In order to find a way to answer this experimentally, we move some manganese atom close to this end. So we put another atom here and then move this atom closer and closer, and now look at the spectroscopic line profiles along this whole system, which is shown here. So this is the case for this topmost situation. So you can see here again these end states, and here are the Yu-Shiba Rusinov states of the manganese atom. And now you can see what happens if I move the atom closer and closer. You basically see that here there happens something to this side of the chain, but on the left side the state basically stays completely unaffected. And this is not at all what you expect from a Majorana states, because they're either you would always have a zero energy end state which is just shifting in position, or you would expect that when you perturb the system here considerably, that also on the left side the system will be affected. We can do the same thing for the niobium substrate. Again, very large minigap. Now in this case, we clearly have non-zero energy end states. And again, you can look at these states in a two-dimensional fashion and look at the length evolution. And again, you can conclude that we have a very large minigap with finite energy end states, but and that these states evolve from Yu-Shiba Rusinov states from the Fermi energy. And again, you can play the same game here, that you perturb the chain from the left side, in this case, with some defect, and you see that these end states are perturbed into two states which have a different energy. So it's clearly not a coherent state, but these are local end states on both sides of the chain. And we can model this by some very minimal tight binding model by just taking into account that in such an antiferromagnetic chain, the hopping between nearest neighbors will be essentially very small, while the superconducting coupling will be large because of this antiferromagnetic spin structure, while the second nearest neighbor hopping will be small, when the second nearest neighbor hopping will be large, and the second nearest neighbor gap superconducting pairing will be small. And if you do this, you end up in such band structures which you can compare to, from the scattering vectors to the data. Yeah, and by this comparison, you can extract exactly the parameters of your tight binding model. This is here the calculation, and this is the data. And then you can look at the local. First, you find that T1 is non-zero because of finite spin-orbit coupling. But the most important thing is that your band structure and model exactly reproduces the experiment. You get these finite energy end states, and so what you can conclude from that, even if in the case of zero spin-orbit interaction, you get trivial edge states, which can be quite close to the Fermi energy. And you always have to be very careful not to confuse this with Majorana modes. And if you want to drive this system into the topologically non-trivial phase, you need a very, very strong spin-orbit coupling, which is unrealistically large. So we think that for this case, to drive the system into topologically non-trivial mode is basically very, very difficult. And I think I just leave this for you to read, and thank you for your attention. Oops.
Thank you very much, Jens, for a very clear and talk, and I can certainly appreciate the experimental efforts that went into that. Other questions in the audience? Please.
I will speak loud. Oh, sorry. There's a microphone. Thanks, Jens, for a beautiful talk. One question I have concerning the Shiba state. Why is there such an asymmetry for the states in the negative and the lower and the upper part of the gap?
Yeah, this is because of that you do not only have this Kondo coupling, but you can also have Coulomb, Coulomb repulsion, and this makes the asymmetry you can show in this very classical model of Shiba. This does your asymmetry, and this is also what helps us in order to distinguish that these bands are in a topologically non-trivial case, because if the two Shiba states would be equal height, then you would basically see two bands which have exactly the same intensity, and then it's again very hard to tell whether your gap is topologically trivial or not. But just that we see that one band with a large intensity crosses the Fermi energy gives us a handle to prove that this is topologically non-trivial.
Can I ask a second short question? Why is the resolution on tantalum so much worse compared to niobium? You maybe said it, but I missed it probably.
Just because the superconducting gap is half as large, and our temperature stays the same.
Thank you.
Yes. Okay, I think in the interest of time we continue, but not before giving you the certificate. Don't walk away.
Thank you very much.
Okay, thank you very much again.